Hi everyone, Marel Gijs Mulders will present in this talk about our recently published paper, A Stellar Mass Dependence of Structured Disks, a Possible Link with Exoplanet Demographics. My name is Nienke van der Marel and I'm a Benting Fellow at the University of Victoria.
And I am Gijs Mulders. I'm an assistant professor at the Adolfo Ibáñez University in Santiago de Chile.
So when we think of ALMA and protoplanetary disks, these beautiful images immediately come to mind. The famous HL Tau image, the D-Sharp survey, both showing a number of disks with rings and gaps at large scales. And of course also the transition disk with large inner dust cavities. So based on all these beautiful images, it seems like gaps in disks are actually really common. And if we think that gaps are caused by planets, this may cause a bit of a problem.
We only know of a handful of planets that have been discovered in these gaps themselves. And if we look at the number of planets discovered with direct imaging at similar separations from the star where we see these gaps, there are actually only a few % of stars that have these planets. So how can we reconcile the large number of gaps that we observe with a low number of directly imaged planets?
Well, the reason for that discrepancy is that there are huge biases in the imaging of protoplanetary disks with gaps. Most of these disks are very bright and very massive because those are the disks that are easiest to image. So if we want to do a proper comparison between exoplanets and protoplanetary disks, we need to correct for these biases by looking at complete disk surveys. And over the last 5 years, many of these disk surveys have been done in the nearby star-forming regions. These are done in so-called snapshot surveys at relatively low resolution of about 0.2 arcseconds, imaging hundreds of disks in the nearby star-forming regions in dust and gas. Here we see a couple of examples of these surveys in Lupus, Ophiuchus, and Upper Sco. And what you can already see from these image galleries is that the majority of these disks are very small in the dust emission. So only a fraction of the disks shows rings and gaps. So one of the things that we have learned from these large disk surveys are insights on evolution, in particular the dust mass evolution. So we see here the cumulative mass distribution of the protoplanetary disks in these regions in different colors. And this plot immediately shows that overall the disk dust mass decreases with age. And this could be related to the evolution of the dust. Another phenomenon that we can study in these surveys is the correlation between disk dust mass and stellar mass. And as it turns out, there is a positive correlation between these two parameters. And we can fit a slope through the dust mass and stellar mass data points. As it turns out, this slope actually decreases with age as well. And what that tells us is that the dust mass doesn't just decrease with age, it actually decreases with age the strongest for the lowest mass stars. So how can we understand all of this? We need to go back to the classical picture of dust evolution. And this was a picture that was already known in the 70s. So if we think of a protoplanetary disk, a smooth protoplanetary disk made of gas and dust, it has a surface density and a temperature that drops radially outwards. And because of that, there is a pressure gradient in the disk. As a result of this pressure gradient, gas particles and also small dust grains will not move Keplerian around the star. They will move a little bit slower on sub-Keplerian orbits. And this is a difference of around 0.1%. It's a very minor difference. But it has a huge effect on the distribution of the dust, because larger dust particles, so particles that have grown to larger sizes, like the ones that we are tracing with ALMA, they are less coupled to the gas. Therefore, they don't feel the pressure gradient. And therefore, they want to move on Keplerian orbits. But they're surrounded by all this gas and small grains that are moving slower. So they experience this as a headwind lose angular momentum and drift inwards towards the star. So this is how we can understand radial inwards drift of the large dust particles. We expect large particles to drift inwards on short timescale. And effectively, large dust particles will always move in the direction of the highest pressure in the disk. For a smooth disk, this is the star. But if you have pressure bumps, for example, at the edge of a planet gap, you can prevent this radial drift from happening. So how does this work in connection with planets? Well, as it turns out, there is a minimum planet mass requirement to carve a gap that has a strong enough pressure bump at the outer edge where dust particles can be concentrated to create a dust trap, or which will be visible as a dust ring. And this minimum planet mass is, depending on the conditions, about 10 to 20 Earth masses. So if we now feed us back into the idea of how a dust disk evolves with time, and this was a very nice work by Paula Pinilla, you can essentially say that we have two types of disks, two types of dust evolution. Either a disk without pressure bumps, it will evolve through radial drift, so the dust mass drops rapidly over a few million years, or we have a disk which contains a planet gap and therefore a dust trap, where the dust will drift towards this pressure bump, towards the dust trap, and then stay there. So essentially, the disk will maintain a high millimeter dust mass in the outer disk, in these dust rings that we are observing. So we can now compare the different morphologies that we see in protoplanetary disks to different types of planets. So we have compact disks which don't show any large-scale gaps, such as CX tau. Such a disk may contain planets, but those planets must be very low mass, because otherwise they would have created these pressure bumps in the disk. And that threshold must be somewhere between 10 and 20 Earth masses. We can think of ring disks with narrow gaps, which probably have planets above 15 Earth masses, or above a Neptune mass, but probably less than about a Jupiter mass. And then finally, we have the third category, the so-called transition disk with these large inner cavities. They must be caused by the most massive planets of more than a Jupiter mass. So with these three categories, we decided to collect the disk data from all the nearby star-forming regions, so from all these disk surveys that have been done with ALMA. This disk survey in the end consisted of more than 700 disks across all nearby star-forming regions. And we classified each disk as either a ring disk, a transition disk, or a disk without structure. And the problem is, of course, that several of these disks didn't have high resolution data. And that means that you cannot actually say whether they have gaps or not. And well, just as an example, there's this disk that was first imaged at 0.3 arcsecond resolution, which just showed that it's rather extended. But at high resolution, it clearly has multiple gaps in the dust distribution. So for the purpose of this study, we are making the assumption that disks that are extended, meaning more than 40 AU in size, can be classified in a fourth category called extended disks. And those extended disks very likely contain gaps and rings as well, simply because there is no way that the dust can be spread out over such large radii without having these pressure bumps. So this is essentially a dust evolution argument to make this assumption. So with this classification, we plot the distribution of the disks, of all these 700 disks, as a function of age. So we group each of the star-forming regions in young, intermediate, and older age. We use this color coding for the different types of disks that we see. And then we essentially just plot the distribution of the dust masses for each of these morphologies. What you notice is that the disks that show gaps, that show substructure, are always located on the high end of the dust mass distribution. And they stay on the high end of the dust mass distribution, while the majority of the disks, which are shown in black or in gray, so these are the compact disks and the non-detections, that dust mass decreases with time. So this provides evidence that there are, in fact, two separate evolutionary pathways, at least for the dust, namely the gap disks and the compact disks. So now how can we compare this with exoplanets?
So we've discovered many exoplanets around older stars. And there are thousands of exoplanets discovered, but as I mentioned before, at these large separations where we see these gaps, we mostly have the most massively planets that we can directly image. However, closer to the star, there are much more planets that we know, and also many more lower mass planets. In particular, radial velocity surveys have mapped the distribution of giant planets down to much lower planet masses. And we can use this planet mass distribution to compare with the number of gaps that we see in these ALMA studies. So this plot shows the planet mass distribution from giant planets from one particular survey from Mayer et al. 2011. And what you can see here is that the smaller giant planets are more common than the larger planets. So the smaller a giant planet can be that opens a gap, the more of these planets there are available to create these gaps. In other words, the giant planet occurrence increases towards the lowest mass planets. So we use this to build a demographical model of exoplanets. So we have the distribution of planet mass, and we combine this with how the occurrence of giant planets correlates with a stellar mass as well. We know that giant planets occur more frequently around higher mass stars. And so we combine these two elements together, the planet mass distribution and the dependence of planets on stellar mass, to construct a demographical model for the giant planet occurrence as function of planet mass and stellar mass to predict how many planets there can be in a certain group of stars.
So now we do a similar comparison, a similar calculation of the occurrence rate in our disk survey. Because also for these hundreds of disks, we know the stellar masses. And what we find, if we plot the number of transition disk, ring disk, and extended disks as a function of stellar mass, that the disks with gaps are most common around the highest mass stars. And we show this here in a pie chart by simply counting the numbers. But we also did a bit more advanced calculation where we fit a power law distribution of this occurrence rate of both transition disks and the ring and extended disks as a function of stellar mass. And indeed, we find that this disk fraction, the gap disk fraction, increases with stellar mass, and that this is a significant correlation. So now, comparing this back with the exoplanets.
So we use our demographical model of exoplanets to predict how many gaps you would expect based on the exoplanet occurrence. So here in the bottom row, we show a prediction where if exoplanets of more than a Jupiter mass are present, it creates a transition disk, and if lower mass planets between 0.2 and 1 Jupiter mass is present, it creates a ring disk. And what's shown here is that because the giant planet occurrence increases with stellar mass, we also predict that there would be more rings and gaps around higher mass stars, which matches very well with what is observed. But now let's take a look at the smaller planets. So the super Earths that have been discovered with the Kepler Space Telescope, for example, their occurrence is actually anti-correlated with stellar mass. These planets are more common around lower mass stars. So how can we connect this with the statistics of gaps that we see with ALMA? One possible explanation is that these planets form in the disks that don't have the observed structures. So here we calculate the fraction of stars that have these super Earths and the fraction of stars that don't have these super Earths. And here in purple, we show that the fraction of stars that don't have these super Earths actually correlate very well with the predicted amount of structures that we see, including a correction for binaries that we applied for Mo and Crater. So in other words, if the super Earths are not correlated with the observed disk structures, this matches very well. And this leads us to an hypothesis where we connect the known correlations between stellar mass, disk mass, and exoplanets, and explain this into a framework of how giant planet formation impacts disk evolution and exoplanet formation. So there are two scenarios. One is where a giant planet forms, and one is where a giant planet doesn't form. In case the giant planet forms, it creates a structure in a disk and prevents the dust from drifting in, so we can observe a massive structured disk that also has a giant planet in it. On the other hand, if a giant planet doesn't form, there's no pressure bumps and the dust will drift inwards, creating a compact disk that could form super Earths, and this will lead to the observed dependence between stellar mass and close-in planets.
So one possible caveat with this scenario is this question about the compact disks, because most of these compact disks haven't been observed at high angular resolution. So we actually cannot confirm that they have no gaps at all. However, there's this interesting result by Banzatti et al. 2020, where they find that the water over HCN ratio, so essentially the amount of water vapor, is anti-correlated with the dust disk size. And they propose a scenario where there are also two different types of disks. There are compact disks where the icy pebbles have drifted all the way inside the water snowline, where the water is evaporated. However, in the disks that are extended, that contain pressure bumps, these icy pebbles are trapped in rings outside the water snowline, and therefore the amount of water vapor will be lower. So even if we don't have the exact measurements of these compact dust disks, this anti-correlation is encouraging for the idea that compact disks really are compact and do not contain any large-scale gaps. So to summarize, based on our study, we propose that there are two evolutionary pathways for gapped and non-gapped disks, which is determined by the presence of pressure bumps. The stellar mass dependence of the occurrence of gap disk matches with that of giant exoplanets, assuming that exoplanets drift inwards, migrate inwards, while the stellar mass dependence of compact disks matches with that of the close-in super-Earths. These results link exoplanet populations, dust evolution, and disk demographics. If you would like to know more, take a look at our paper and feel free to email us with any questions. Thank you.